Hi everyone and welcome to another video, and this is still differentiation. So today I'll be showing you about the derivatives of trigonometric functions. So I'll be dealing with trigonometric functions themselves and also inverse trigonometric functions all in the same video. So it'll be one package, so one big load for you to learn. Alright, let's learn how these work in today's video. Alright, so we continue from where we stopped. So today we're going to be moving on to derivatives of trigonometric functions. So now this video is more of a follow-up to we've done first principles before to do with other kinds of functions, but now the best way we're going to derive these trigonometric functions to see how they are proved is by using first principles also. So let's look at this first example. So we're being told to differentiate sine x from first principles. So how do we solve this? So we're going to let y to be equal to sine x, and then like we've done before, where there is a y we're going to replace that with y plus change in y. Then where there is an x we're going to replace that with x plus change in x. So now we can see that if we make change in y the subject, so it's going to be equal to sine of x plus change in x minus y. But remember that y is sine x, so we're going to replace it there. So now from our knowledge of compound angles, we know that we can expand a sine x plus sine plus change in x, and this is how it is expanded. So it's expanded and it becomes sine x cos change of x plus sine change of x cos x minus the sine x. Then next what we're going to do is we can actually see that we have sine x here in common. So we have sine x here and sine x here, so we're going to factorize that out. So when you factorize it out, this is what we end up having. Alright, and then next we're going to remember, and this is going to be one of the most important knowledge in this section. Now when we're dealing with small angles, because we've been mentioning that the changes are actually small, so change in x and change in y are actually very small values. So for small angles measured in radians, sine of change in x is approximately equal to change in x, and then cos change in x is also approximately equal to 1. So we're going to substitute that in, so we can see where there is a cos change in x, we've placed there 1, and then where there is a sine change in x, we've just replaced that with change in x, and that's what we have. But 1 minus 1 is 0. So we have a 0 times sine x, and we know what's going to happen there. So that's a 0. So we remain with change in y being equal to change in x cos x. Now the next step is going to be to multiply both sides by 1 over change in x, so that we actually create the slope formula, so that we have change in y over change in x. So that's going to be equal to change in x cos x over change in x. So now we can see that the change in x values are going to cancel on the right hand side, so we're going to remain with change in y over change in x being equal to cos x. But dy dx is going to be equal to limit of that, and we can see that we're going to approximate and we're going to replace the value of change in x with 0. But good enough, in this example we don't have any change in x remaining on the right hand side, so we're just going to substitute the value of change in y over change in x, the slope formula, with dy dx. So dy dx is going to be equal to cos x. So hence when we differentiate sine x, the answer is equal to cos x. Alright, so moving on to question number 2. How about if we ask to differentiate cos x from first principles? So we're going to let y to be equal to cos x, and then next we're going to have y plus change in y being equal to cos x plus change in x. So where there is a y, we put y plus change in y, and then where there is an x, we put x plus change in x. So we can say that change in y shall be equal to cos bracket x plus change in x minus y. But remember that y is cos x, so we're going to substitute that in there. Then we're going to expand the cos of those values in brackets using the knowledge of compound angles. So now those brackets expand to cos x cos change in x minus sine change in x sine x minus the cos x. Now we're going to collect like terms, actually not really like terms, but values that actually have something in common. We can actually see that there is a cos x here and a cos x here, so we're going to bring those terms together as we had just done there. Then we're going to factorize out the cos x, and that's what we're going to have. Then we're going to remember that for small angles measured in radians, sine change in x is approximately equal to x, and cos change in x is approximately equal to 1. So we're going to substitute those inside there. But now at 1 minus 1 is 0. So 0 times cos x is 0. So we're left with negative change in x sine x. Now next, we're going to multiply both sides by 1 over change in x to create the slope formula, change in y over change in x. So now we're left with negative sine x on the right hand side. So now, we remember now we're going to introduce the dy dx, and then dy dx shall be equal to negative sine x. So therefore, the derivative of cos x is negative sine x. Alright, let's move on to question number 3. So we're being asked to differentiate tan x from first principles. So we're going to let y to be equal to tan x. Now, to work out this one in an easy way, we're going to convert the tan x into sine x over cos of x. So now, wherever there is a y, we're going to put y plus change in y, and wherever there is an x, we put x plus change in x. So now, we're going to make change in y the subject, so we're going to subtract a y on the right hand side, but y is equal to sine x over cos x. So that's what we have right there. Alright, so next we're going to find the LCM. So the LCM is going to be cos x, cos bracket x plus change in x. So we can actually see that this value that we actually have here, divide by this, is going to be equal to cos x. Cos x is going to multiply the value right there. And then this value here, the LCM divided by cos x, we're going to be left with cos x plus change in x times sine x. So that's what we have right there. And then now next we can actually now open these using the knowledge of compound angles. So this is going to expand to that, and then this is going to expand to that value right there. So next we're going to open brackets. So when I open brackets, this is what I end up with, and that's what I end up with right on the other side. So I've actually also opened brackets for the denominator, and then I also have the same thing. Now as you can see, there are some values that actually reduce. So this and this cancel, and then I'm left with, right, so these two values cancel, so this and this cancel, so I'm left with that. Alright, so next we're going to remember that for small angles measured in radians, sine change in x is approximately equal to change in x, and then cos change in x is approximately equal to 1. So with that knowledge, we're going to substitute in those values. So now you can see we had sine change in x at the numerator, so now that we have it on both sides, and then also at the denominator we've actually substituted the values, and where there was cos change in x we actually put a 1. Right, so we can factorize out the value change in x. So now next we can actually see that this is what we're left with, because cos squared x plus sine squared x is equal to 1. Now multiplying both sides by 1 over change in x, we can actually see that now we'll have change in y over change in x is equal to 1 over that value. But we know dy dx is going to be equal to that. So now wherever there is a change in x, we're going to approximate that value to 0. I think now it's safe, because now I can see we can avoid having the denominator, the final value of the denominator as being equal to 0. So it's actually now safe to make change in x and approximate it to 0. So this is what we have now. So we shall be left with dy dx being equal to 1 over cos squared x, and we know that 1 over cos squared x represents sec squared x. So therefore the derivative of tan x is sec squared x. Alright, so moving on to question number 4, we're being told to differentiate sec x from first principles. So how do we solve this? We're going to let y to be equal to sec x, but remember that sec x can be represented as 1 over cos x. So now, wherever there is a y, we introduce a change in y, and then wherever there is an x, we introduce a change in x. So now, making change in y the subject, this is what we end up having. So we remember that y is 1 over cos x. So we substitute that there, so we get the LCM. So the LCM right here is going to be equal to that. So this divide by that is cos x, that's why I have the cos x here, times 1 is cos x, and then this divide by that is cos x plus change in x. Multiplying that, that's what we remain with. So now we're going to open now these brackets using the knowledge of compound angles from trigonometry. Then this is what we get from the expansions. And then when you open the brackets, you can actually see that this minus sign affects this, and we have a plus sign. Then this is what we end up with at the denominator. Alright. So now there are some items that are common. So now we see cos x here and cos x here, so we can factorize out the cos x value, and that's what remains with cos x into 1 minus cos change in x. Now remember that for small angles measured in radians, sine change in x is approximately equal to change in x, and cos change in x is approximately equal to 1. So now we're going to substitute those values there, and as you can see now we are left with 1 minus 1 in those brackets. So 1 minus 1 is 0, and then we are left with that, because 0 times cos x is 0. So we're left with change in x sine x. The denominator, that's actually what we have. So now we can multiply both sides by 1 over change in x, and this is what we end up having. So now we have the slope formula, change in y over change in x. Alright, so now next I see it's actually safe to actually introduce the approximate change in x to 0. So remember that dy dx is that. So now wherever there is change in x, we put a 0, and where there is the slope formula, change in y over change in x, we're going to substitute that with the dy dx. So now we're left with sine x over cos squared x, but also remember this can be split as sine x over cos x times 1 over cos x, and then not sine x over cos x is tan x, and then 1 over cos x is sec x. So therefore the derivative of sec x is tan x sec x, and that is what they wanted. Alright, so moving on, we're going to differentiate cosec x from first principles. So now we're going to let y be equal to cosec x, then we know that y is equal to 1 over sine x. It can also be represented that way. So now we're going to introduce the change in y. So y plus change in y is equal to 1 over, so wherever there is an x, we introduce the change in x. And then now change in y shall be equal to that minus y. But remember that y is equal to 1 over sine x. So now we're going to find the LCM. So the LCM is going to be equal to sine x, sine bracket x plus change in x. So when you get this value, divide by this, we are left with sine x. And then sine x times 1 is sine x, and then this value divided by this, we are left with sine x plus change in x multiplied by 1, and we are left with that. So next we're going to move on and expand everything by the knowledge of compound angles from trigonometry, and that's what we have. So now next, remember that when you open brackets, this minus affects this positive, and we are left with a minus. Then now next we can actually see that we can actually factorize out a sine x right here. Then that's what we're actually left with. So now we can introduce the knowledge that for small angles measured in radians, sine change in x is approximately equal to change in x, and cos change in x is approximately equal to 1. So now we will be left with that. So now at the numerator, we'll be left with negative change in x cos x. So now next we can actually now multiply both sides by 1 over change in x, and this is what we are left with. So now we have the slope formula, y over change in y over change in x being equal to negative cos x divided by sine squared x plus change in x sine x cos x. So now next we can actually introduce the dy dx and approximate the x value to 0, and I believe now it's safe. So now we'll be left with that. So now we're left with negative cos x divided by sine squared x, which can also be split as negative cos x over sine x times 1 over sine x, of which a negative cos x over sine x is a negative cot x, and then 1 over sine x is cosec x. So therefore the derivative of cosec x is negative cot x cosec x, and that's what the answer that they wanted. Alright, so next we're going to differentiate cot x from first principles. So remember that we're actually going to first let y be equal to cot x. So remember that y represents that cos x can also be expressed as cos x over sine x. So now we're going to introduce the change in y and the change in x. So where there is a y, we introduce a change in y, and where there is an x, we introduce a change in x. So now we can make change in y the subject, and then that's what it's going to be equal to. But remember that y is cos x over sine x. So now this is what we end up having. So now next we're going to find the LCM. So the LCM is sine x sine bracket x plus change in x. So when you get this value here, divide by this, we are left with sine x. So we have sine x multiplying this. So that's what we have. Then when we get this divide by sine x, we are left with this. So we will get sine x plus change in x times cos x, and that's what we have right there. So now we can open up with the knowledge of compound angles. We can actually expound everything in brackets. Then when we simplify and open brackets, we can actually see what happens. So actually this negative affects everything here. So it's going to be a negative, a minus also. Alright, so now next we can actually see that there's some values that cancel. So this and this cancel, and we're left with these values. But remember that for small angles measured in radians, sine change in x is approximately equal to change in x, and cos change in x is approximately equal to 1. So therefore, change in y shall be equal to that. So now we can actually factorize out the negative change in x, and inside the brackets we are left with sine squared x plus cos squared x, of which now those are equal to 1 from the knowledge of trigonometry. So we're left with that. So therefore now we can multiply both sides by 1 over change in x to now actually create the slope formula, of which the slope formula is change in y over change in x. So now on the right hand side we're left with the negative 1 over sine squared x plus change in x sine x cos x. So now we're going to approximate to 0, we're going to approximate the change in x and equate it to 0, and then we're going to introduce the dy dx. So therefore dy dx shall be equal to that. So now dy dx is equal to negative 1 over sine squared x, of which that's definitely equal to negative cos x squared x. So therefore the derivative of cot x is negative cos x squared x, and that is what they wanted. Alright, so in summary, the derivatives of trigonometric functions are: the derivative of sine x is cos x, the derivative of cos x is negative sine x, the derivative of tan x is sec squared x, the derivative of cosec x is negative cosec x cot x, and then the derivative of sec x is negative, is sec x tan x, and then the derivative of cot x is negative cosec squared x. So that's it in summary. I encourage you to memorize this and have them in memory, so that every single time we do numbers from here we'll actually speed up the process. Alright, now let's look at some more tricky examples to just take this a little bit to a topper notch. So we're being told to find dy dx if y is equal to sine cubed 5x over 6x squared. Now this requires more logic, but this is actually easy to solve. So now you can see that this is what y represents. So now, first of all, this is actually an example that actually includes two different ratios of two different functions. So basically we're going to be using the quotient rule. So now we're going to let u to represent the value on the numerator, so u is going to be equal to that. But this is how I prefer to represent my value. So I would rather have the cubed value outside the brackets, but it basically means the same thing. So u is going to be equal to sine 5x bracket cubed. So we get du dx by chain rule. Now this is an example, so this is more of a, so this actually requires the chain rule to solve, because it has actually a double angle involved. So by chain rule, we're going to use chain rule to get the value of du dx. So we're going to let t be equal to sine 5x. So that means that dt dx is 5 cos 5x. So basically, remember, like I mentioned before, that the easiest way to actually understand this is when you differentiate this, you differentiate the values that you have here. So we have 5x. So 5x, when it's differentiated, you get the answer 5. So we're going to bring that 5 to the left hand side of the variable. Then when you differentiate a sign, we get cos. So that's now what we end up with, 5 cos 5x. So that's the quickest way of doing that, but actually it would actually require to do another chain rule again, but that's how we speed up the process. So now u is going to be equal to t cubed, of which du dt is 3t squared. So from chain rule, du dx shall be equal to du dt times dt dx. So du dx shall be equal to 3t squared times 5 cos 5x. But remember, t is sine 5x, so we end up having du dx being equal to 15 sine squared 5x cos 5x. So now that we know what du dx is, now we can deal with the v value. Now we're going to let v represent the denominator, so v is going to be equal to 6x squared. So dv dx is 12x. So now that we know what dv dx is, what du dx is, what u is, and what v is, we're going to now use the quotient rule. So now we're going to substitute the values to the quotient rule, and this is what we end up having. Now when we expand this, we can actually see that this squared and that squared, so it's going to be ending up with 36x to the power 4. And then right here, when we multiply the different values, 15 times 6 is 90. So we remain with 90x squared in times sine squared 5x cos 5x minus 12x sine cubed 5x. Then now we can actually see that now we can factorize out some values from the bracket. So we can actually factorize out 6x sine squared 5x, and that's what we're left with in brackets. And then as you can see that some values will reduce from here, then we shall be left with that. So the 6 reduces with the 36, and we're left with a 6 at the denominator. Then the x values reduce, and we're left with x cubed at the denominator. And that's actually the answer that we're looking for, and that's actually our proof of what dy dx is. Alright, so moving on to the next question, we're being told to find the derivative of cos 2x over 1 plus sine 2x with respect to x. So let's solve this. So remember that now we're going to let y be equal to that. So this is an example that definitely requires the quotient rule, because we're dealing with the ratios of two different functions. So now we're going to let u be equal to cos 2x, but also remember that now when we differentiate du dx, the answer is going to be equal to negative 2 sine 2x. Then when we let v be equal to 1 plus sine 2x, dv dx shall be equal to 2 cos 2x. Then now from quotient rule, we're going to substitute in the values. So this is how they're going to look in a more simplified way. And then now when we open these brackets here, we shall actually see that now we have negative 2 sine 2x minus, because this negative affects this positive sign, minus 2 sine squared 2x minus 2 cos squared 2x. So now we can actually factorize out the negative 2 from here. Then we're left with sine squared 2x plus cos squared 2x, of which from our knowledge of trigonometry we know this will actually be equal to 1. Alright, so next now we can actually see this is what we're left with. So I can now factorize out the negative 2 from the numerator. Then as you can see that now these two values are similar. So this is slightly similar to this. So there's going to be a reduction. So now we have negative 2 over 1 plus sine 2x. And that is our derivative. Alright, so moving on to number 9. So this is a question from UNEB 2004, and this was question number 4. So we're being told that given y is equal to root 1 plus sine x over 1 minus sine x, show that dy dx is equal to 1 minus sine x. So how do we solve this? So we have that. So now this number is going to be a little bit challenging unless we find a way of eliminating that root quickly. Alright, so to eliminate the root, we're going to rationalize the denominator. And then that's what we're going to do. So now we're going to multiply both the top and the bottom by 1 plus sine x. So now this is what we end up having. So we have 1 plus sine x bracket squared over 1 minus sine squared x. So remember, when rationalizing the denominator, it means multiply both the top and bottom by another value that actually has a different sign from what we actually have right there. Then this is what we're left with. So now we know that 1 minus sine squared x is equal to cos squared x. And then here, these two values multiplying each other create a squared. So now we have that squared. So now you can see that now the root will cancel with this and that. So now we'll be left with y being equal to 1 plus sine x over cos x. So now this is now where we can now apply the quotient rule. Alright, so now we're going to apply the quotient rule. So when you apply the quotient rule, this is what you end up coming with. So now we end up having a cos squared x at the top plus sine x plus sine squared x over cos squared x. Then you can actually see that now when you bring the cos squared x plus sine squared x together, we know what that represents in trigonometry. They represent a 1. So you have a 1 plus sine x over cos squared x. But actually we've not yet proved what we actually wanted. So now we're actually going to continue simplifying even further. So now we need to make it look like the proof we've been given. So now remember that in our final proof there is a 1 minus sine squared x. 1 minus sine x somewhere. So now we're going to change the cos squared x into a sine. So now we have 1 plus sine x being equal over 1 minus sine squared x. But now you remember that now from difference of two brackets, this can actually be converted into that. So they are actually similar. As you can see that this and this will cancel, and then we are left with dy dx being equal to 1 minus sine x. And that is what they wanted in the proof. Alright, so now next we move on to the derivatives of inverse trigonometric functions. So let's look at how these work. So imagine you're given a question, differentiate sine inverse of x. So this is an inverse trigonometric function. So how do we solve this? So now we're going to let y be equal to sine inverse of x. And then now we know that from the knowledge of inverses, we can actually say that we can actually take the sine x to the left hand side. So this is the same as sin y being equal to x. And then now we're going to apply some of our knowledge from implicit functions. So now we're going to differentiate both sides. So now this value has a y, this value has an x. So now we know that when we differentiate sin y, it's going to be equal to cos y. But when you remember that when you differentiate anything that has a y, when there is an x involved with respect to x, so we're going to multiply what we have here by a dy dx. So that's why we have dy dx multiplying cos y, and then this side, when you differentiate x, it's basically going to be equal to 1. So this knowledge will make sense if you look into implicit functions, which is a topic we've covered already. So that's what actually happens. So now when you make dy dx a subject, you know that it's going to be equal to 1 over cos y. So now we need to eliminate the y value now to get a better value of. So now we need to express our dy dx with an x value. But now it's not going to be that easy, so we're going to have to first do something. Now remember, from trigonometry, of course, we know that cos squared y plus sine squared y is equal to 1. So that means we can also say cos squared y is equal to 1 minus sine squared y. So now we can represent cos squared y with 1 minus sine squared y. But also, we know that if we decide to introduce a root to both sides, we'll have cos y being equal to root of 1 minus sine squared y. So now wherever there is a cos y in the value of dy dx, we can actually represent it as root over 1 minus sine squared, root 1 minus sine squared y. So we can actually do that, but we remember that sin y is equal to x. So where there is sin y, we're going to represent that with an x. So that's why we have a root, cos y being equal to root of 1 minus x squared. So therefore dy dx shall be equal to 1 over root of 1 minus x squared. And that's actually that's the derivative of sine inverse of x. And then how about if you have to differentiate cos inverse of x? How do we do that? So now we're going to do the same thing as we've done in the former number. We're going to let y be equal to cos inverse of x. So cos y shall be equal to x, as you can see, and then dy dx definitely is going to be equal to, so on the left hand side we're going to have a dy dx times negative sine y, because the derivative of cos y is a negative sine y, being equal to 1, because the derivative of x is 1. So dy dx shall be equal to negative 1 over sine y. So from sine squared y is equal to 1 minus cos squared y, we know that sine y shall be equal to root of 1 minus cos squared y. But cos y is equal to x, so therefore sine y is equal to root 1 minus x squared. So therefore dy dx shall be equal to negative 1 over root 1 minus x squared. And that's the derivative of cos inverse of x. How about if we're told to differentiate tan inverse of x? How do we do that? So this is how we do it. So we're going to let y be equal to tan inverse of x. So tan y shall be equal to x. So we also know from the knowledge of implicit functions that now when you differentiate this, tan y, it's going to be equal to sec squared y, but because we're dealing with the y value, we're going to multiply to it a dy dx. Then on the right hand side, we have x, which is going to be equal to become 1. Then, so therefore, if we make dy dx a subject, we have 1 over sec squared y. But also from the knowledge of trigonometry, we know that sec squared y is equal to 1 plus tan squared y. So therefore, we also know that tan y is equal to x, so we end up having sec squared y being equal to 1 plus x squared. So therefore, dy dx is equal to 1 over 1 plus x squared. And that is the derivative of tan inverse of x. So in summary, the derivatives of inverse trigonometric functions are the derivative of sine inverse of x is equal to 1 over root 1 minus x squared. The derivative of cos inverse of x is equal to negative 1 over root of 1 minus x squared. And then the derivative of tan inverse of x is equal to 1 over 1 plus x squared. So now, let's look at other questions. So what if you asked to differentiate cos inverse of 1 minus x squared over 1 plus x squared? How do we do this? So now we're going to let y be equal to that. Then we also know that now we're going to have cos y being equal to that value. So now when we're going to differentiate, the values on the right hand side and the values on the left hand side separately. So now on the right hand side, basically we can actually say we're going to use quotient rule, and then the left hand side, this is actually direct. The derivative of cos y is negative sine y. But because we're dealing with the y value here, from implicit differentiation, we also know that now we're going to multiply that to dy dx. But now let's deal with the right hand side mainly. So let's apply the quotient rule on the right hand side. As you can see, when we apply the quotient rule on the right hand side, this is what we actually have. And then here, as I've mentioned, we have negative sine y times dy dx because of the y value. So now basically we're going to make dy dx the subject, and then this is what we end up having. Then we can open the brackets in the numerator, and that's what we have. And then we can actually see that this and this add, and we have negative 4x. And as you can see that this and this also cancel. So we're left with dy dx being equal to negative 4x over sine y over 1 plus x squared squared. But we cannot leave a y value in our final answer, so we'll actually have to change that. So what are we going to do? So we're going to have to find a way of replacing that. But as you can see, these negatives cancel, and that's what we have. So now we have to find a way of changing this and changing it into a value that actually has x. So what are we going to do? So we're going to have to also remember something. So from trigonometry, we know that sine squared y is equal to 1 minus cos squared y. So we also know, we actually know what cos y represents. So we're going to substitute that in there. Where there is a cos y, we're going to represent it with this value because of remembering that. So now this can actually be represented that way. So this square actually multiplies both, and this is what it actually represents. So sine squared y shall be equal to that, and then we can actually see that we can actually get the LCM here. The LCM is that, and then this divided by 1 is itself times 1, so that's what we have there. And then we know that this divided by itself is 1, so this actually remains as it is. And then next we're going to actually expand these brackets, and this is what we end up having. Then also expand this, and this is what we end up having. But be careful because there's a minus sign here, and that's what we actually have to be careful about. So as you can see, when you open brackets, this is what we have. So we have a minus 1 plus 2x squared minus x power 4. And as you can see, some values cancel, this and this cancel, then this and this add, the ones cancel, so we have 4x squared at the numerator. But now we actually can now simplify this because we're looking for a value of sine y. So sine y is going to be equal to the root of the values on the right hand side. So therefore sine y shall be equal to 2x over 1 plus x squared. So now we can substitute that. So therefore dy dx shall be equal to 4x over 2x over 1 plus x squared times 1 plus x squared squared. So now let's simplify this a little bit further. So when you simplify it a little bit further, we can actually see that this and this reduce, and we're left with 2x into 1 plus x squared. But we can also reduce that further. We can actually see that 4x divided by 2x is 2. So we have a 2 in the numerator, and therefore our final answer for dy dx shall be equal to 2 over 1 plus x squared, and that is what we are looking for. Alright, so now how about if we ask to differentiate tan inverse of 1 minus x squared over 1 plus x squared? So again, we're going to let y be equal to tan inverse of that. So tan y shall be equal to 1 minus x squared over 1 plus x squared. So when differentiating, we're going to apply quotient rule on the right hand side. Okay, now we know on the left hand side definitely the derivative of tan y is sec squared y. But because we're dealing with the y value here, from the knowledge of implicit functions, we're going to multiply a dy dx to it. And then on the right hand side, we've applied quotient rule, and this is what we end up with. So now when we open those brackets, that's what we end up with. So you can actually see that this and this cancel, and we're left with negative 4x on the numerator. So now we need to find the final value of dy dx, but we can't have this y in our final answer. So we need to find a way of eliminating that. So from trigonometry, we know that sec squared y is equal to 1 plus tan squared y. So now we're going to substitute these values here because we know what tan y is represented with. So now sec squared y shall be equal to 1 plus that. And then now we can actually introduce the squared into both the numerator and denominator. We can now next find the LCM. So the LCM is that, and then next we can actually expand and open the brackets. This is what we're left with. So now we can actually see that this and this cancel, then this and this add. Actually, you can see now we have 2 plus 2x power 4 at the numerator. Alright, so therefore Remember, all we're looking for was x squared y, and now we have it. So therefore we have a negative 4x divided by that, and then we can actually see that this and this totally cancel, and then we are left with dy dx being equal to negative 4x over 2 plus 2 plus 2x power 4. And now we can see that we can factorize out a 2 in the denominator, then reduce that with the numerator, and we have a negative 2x and the numerator, and then at the numerator now we'll be left with 1 plus x power 4, and that is actually what they wanted. Alright, so now I have an exercise for you. You can actually try these numbers out to see how good you are at the derivatives of trigonometric functions. I believe after you try this, just compare your answers to what I have, and I believe if you have the same answers, it's actually a sign of progress. So actually just try this out and just improve your knowledge of derivatives of trigonometric functions. So I know there are quite a good number of numbers, there are actually many, but I believe that this is for your good, and they'll prove that you actually have understood what we've learned in this chapter. Thank you for watching. Thank you so much for watching this video. I hope the video really helped you. If it did, feel free to share the video with all your friends and help as many as you can. And then if you really like the video, feel free to give the video a like or a thumbs up, and then tell me in the comments if the video really helped you, and I'll try to get time and reply to your comments. And then if you're new to this channel, I encourage you to join the community by subscribing, and then make sure to hit the notification bell so that you get updated every single time I upload a new video. Thank you so much for watching, and I'll see you in my next video.